That first point, that is why do we need non-conventional machining processes. Then we have talked covered that how to classify our different non-conventional machining processes. Okay, then last lecture we have gone through that different characteristics of conventional and non-conventional machining. Okay, and needs of or needs for non-conventional machining. Today we will start the overview of non-conventional machining processes, or I can say overview of advanced machining processes. Now overview means what? I will explain you basic working principle of each and every non-conventional machining process. Each and every non-conventional machining process means what? I will cover AJM, WJM, AWJM, USM belongs to the mechanical energy based processes. Okay, then electrical discharge machining, which is belongs to the electric energy based processes. Okay, so these all processes we are going to see in detail in chapter number 2 and 3. Okay, then after this we will cover the again overview of remaining processes. Remaining processes what? Thermal energy based or thermoelectric based. That means laser beam machining, electric beam machining, plasma arc machining, ion beam machining, and then at last we will see the chemical machining and electrochemical machining. Okay, so these 14 processes and it's a overview today we will cover. Okay, so now again for the sake of simplification I have just divided this lecture into two parts. Part 1, in this part 1 I'm going to cover the mechanical energy based processes and EDM. Okay, so here we'll start with the first. Okay, that is a mechanical energy based processes, that is AJM, WJM, AWJM. Okay, and it's a overview I will start. Now whether this PPT is visible to your diagram, can anybody say yes or no?
Yes, sir. Yes.
Okay, no problem. So now let us see the working principle of some of mechanical energy based processes. Now let us take some examples of our day-to-day events, or I can say incidents, okay, which we see in our daily life. Now in this particular figure, that means figure number 1, okay, WJM. In this particular figure, this figure is very interesting. Now see here, if you see in this particular figure, water is coming from the tap. Okay, water is coming from the tap. Okay, I am highlighting also that direction. Water is coming from tap, and all of you have the tap at our home, houses, correct? And the water is coming. And suppose if you put the wooden piece under this tap. Okay, wooden piece is placed under this tap. Okay, now from this tap or from this pipe I can say water is coming, and under that and I have kept the wooden piece. Okay, that is your work piece, you can say. Then after few days what will happen? Okay, suppose there is one tap, from that tap water is flowing, and below or under that tap you have placed the wooden piece. Then after a few days, or I can say after 10 days, 15 days, or at max 1 month, what you will observe? Can anybody guess? What will happen? In Marathi, I will tell. पाण्याच्या नळाखाली जर आपण लाकडाचा ठोकळा जर ठेवला तर काय होईल एका महिन्यानंतर किंवा थोड्या दिवसानंतर? हा, प्लीज reply me. What will happen, or what you will observe? Okay, because perspective of everyone is maybe different. काय होईल सांगा? किंवा आपल्या घरात I will take another example. Okay, जर आपल्या पाण्याच्या नळाखाली आपल्या हे असं म्हणतं का कोबा केला आपण म्हणतो सिमेंट किंवा जरा पश्चिम. ओके, कंटिन्युअसली जर त्या नळापासून कंटिन्युअस एक ड्रॉप असं खाली थेंब थेंब सांडत असेल तर एक धरून झालं एक महिना एका वर्षानंतर तुम्ही काय तर असं खड्डा पडलेला ऑब्झर्व करता का?
Yes, sir.
Okay, that means due to the kinetic energy of that water droplet and continuous impact of that water droplet on that workpiece. Now that workpiece means for our wooden block, or you can take the another example. So due to that impact, erosion of that workpiece material or the erosion of that wooden block will happen. And due to that erosion, small particles will start to remove from that surface, and that small particle, here I will say scatters. Okay, that small particle which is going to remove from that surface, it is called scatters, or I can say debris. Okay, debris. Okay, these are the two terms which we are going to use in our subject. Scatter means what? Small particles which is removed from the surface of workpiece, or you can say debris also, small particle. Okay, tiny particle. Okay, so now you got the basic, because this example is our in the day-to-day life event. Okay, now the question arises how water is. Okay, you got the some amount of material, I can say scatters will be removed. Okay, or that scatters will be from on that surface. Scatter means what? Small particles which is removed from that surface due to the impact of water droplet. Now the question arises how water is able to cut the wood. Okay, how water is able to cut the wood, because we have just studied that in conventional machining we know that tool material should be harder than the workpiece material. Okay, am I correct? Tool material should be harder than the workpiece material. But if you take this example, okay, if you compare the water and the wooden piece, definitely wooden block is harder than the water. Then, but just you observe after few days that due to that water impact of water droplet, material removed from the work surface. Work surface means wooden surface. So that this question is arises how the water droplet or water is able to cut the wood. Correct. Now, so as just I mentioned, tool material should be harder than the workpiece material. Then there is nothing like this tool only water is coming falling on the woods, and still it is able to create the scatter. Scatter means that small droplet, and over the if you can see here also. Okay, that scatter I have shown here, small scatters are here. Correct. Now another example, if I will place lump of soil, okay, lump of soil under this tab. Okay, instead of water, now I have kept the lump of soil. Okay, then you will find that again this crater is bigger than the crater that has been observed or that has been formed in this on this wooden surface. Okay, I repeat, scatters means tiny particle or small particles which are removed from that workpiece. Okay, so if you take the example of lump of soil and it is kept or put under this tab of water, after few days or after few times, you will observe that you will get small scatter will be found on this surface. Okay, and material removal happen from this lump of soil. Okay, now again question arises how this water is able to remove the material from the wood, or I can say from the soil. Correct. So keeping this in view, the destructive phenomena, keeping this in keeping this phenomena in destructive manner, I will ask one question to all of you, that could you think to make this destructive phenomena for utilization or for the developing the new technology? Okay, this is just the example where we are observing in each and our daily life. Okay, for our daily event. So this destructive phenomena we have to apply for the advancement of our machining processes. Okay, so I am saying this is a destructive phenomena. Okay, but again this destructive phenomena you have to use or you have to apply in the sense of constructive purpose. Okay, constructive purpose means what? by thinking the technical view. Okay, and for some constructive purposes, then people started thinking, and people took, I can say, people took the inspiration from this destructive phenomena, and they have developed the process. It is called water jet machining. Okay, what they people did, they have just taken this, I can say, taken this destructive phenomena, and these the people have developed the constructive solution. Okay, constructive solution for the, or I can say constructive purpose, and this process is called water jet machining. Okay, in simple language I will tell, water आपण काय करायचे, with high velocity we have to strike, or we have to impinge that water on the workpiece, and due to the kinetic energy of that water, material removal will happen from the workpiece material. Okay, now how that material will happen, material removal will happen due to the erosion of the material. Okay, workpiece erosion. Okay, now how that erosion will start, due to the impact, or I can say due to the kinetic energy of high jet velocity of water, high jet velocity. Now as we have to strike the water with high velocity, okay, on the workpiece, so for that purpose we have to use the nozzle. Okay, in upper terminal subject you learn about the nozzle. Okay, small diameter. Okay, or convergent section and divergent section. Okay, so I'm not going to go about more about the nozzle. Okay, to get the high velocity of water jet, we are going to use the nozzle. Okay, understood? Here kinetic energy of water is used for erosion action. Erosion action means what? Material removal action. Huh? Okay. Now now the question arises, what will be the speed of that water? What will be the speed of that water? Okay, so you can keep velocity of this water jet as high as 900 meter per second. Please note down this. Velocity of water jet you can keep as high as up to, or I can say as high as 900 meter per second. In university exam or in our college ISC exam also, this MCQ will ask. Okay, velocity of water jet. Okay, in water jet machining. Okay, understood? Simple phenomena. It is used by the researcher, I can say, and they have developed this process, water jet machining. Very simple. Okay, understood? If you understood this, then remaining two that are very easy to understand, because same process we are going to continue. Understood this water jet machining? Say yes or no.
Yes, sir.
Okay. Now
Yes, sir.
we'll move for the next one. Okay, water jet machining I have covered. Now the same way. Okay, in same way, in rainy season, if you see that water coming out of the tap, okay, in the rainy season water is coming out of the tap, and you will find some sand particles are there, or are mixed with that water. Here water is coming through this tap, and in that water, due to the rain, I can say due to the rain, small sand particles are also mixed. Okay, now once again what I will do, I will take workpiece which is made up of the stone. Okay, stone I will consider as a workpiece, and I will put under this tab. Okay, I have put that stone under this tab. Okay, through this tab, water along with or mixed with sand, you will get that fluid jet. I will say fluid jet, because fluid jet here I will consider mixture of water and sand particle. Okay, now when the same particles along with the water jet, that means same particles what? Sand particles along with jet, they will come and strike the stone. Then after I will say few days or few months, what will happen? Okay, what will happen? Can you guess what will happen? Whether that stone surface that will be the remain same, okay, or I can say plain, or due to impact of water plus sand particles, whether small craters will form on that surface. What will happen? Pranay, स्टोनचा
Crack पडतील त्याला सर.
त्याला क्रॅक पडतील म्हणताय का तुम्ही, का त्याचा वरच्या सरफेस वरचा स्मॉल पार्टिकल बाहेर पडतात, म्हणजे मटेरियल
स्मॉल पार्टिकल बाहेर पडतील, स्कॅटर.
हा हा स्क्रॅटर नाही, क्रॅटर CRATER scatter. Okay, or you can say debris also, no problem. Okay, so due to the again same phenomena, जे आपण वॉटर जेट मशीनला फेनॉमेना वापरला तेच वापरलाय, फक्त इथे मी काय केलंय, त्या वॉटर मध्ये सँड पार्टिकल मिक्स केले. ओके, आणि हिअर आय हॅव टेकन द नॉर्मल एक्झाम्पल, दॅट इज अ रेनी सीजन एक्झाम्पल. ओके, same phenomena. Okay, due to the kinetic energy of water, or that I can say here fluid. Now that fluid means what? Water plus sand particle. Now for that sand particle I will say abrasive particle. I will say abrasive particle. Okay, and that mixture of water abrasive particle and kinetic energy of that jet which will strike on the stone, due to that erosion will happen and craters will be formed on this surface. Okay, that means material removal happen. Okay, again this is our in general example, correct? So researcher, or I can say people, started thinking about this destructive phenomena. I will say started thinking about this destructive phenomena, and they have used this phenomena for the constructive purpose. For the constructive purpose. Now constructive purpose is what? For the machining of the different materials. Okay, now that what are the purpose or constructive purpose they have utilized this phenomena. So that new process they have given the name as abrasive water jet machining process. Okay, मगाची होते ते वॉटर जेट मशीन होते, आता abrasive water jet machining आहे. का? फक्त फरक एकच, त्या वॉटर मध्ये आपण फक्त abrasive particle मिक्स केले. That's it. Okay, सेम इथं आहे kinetic energy of this flowing fluid or jet. I will say jet kinetic energy. Okay, that kinetic energy is the form of energy which is required for the erosion action, and due to that erosion means what? Material removal happen from the surface of your workpiece. Now here workpiece is what? Stone. Now you take another example. Instead of this stone, you can put the workpiece made up of the aluminum and put under that tap. Okay, and from that tap water plus abrasive particles will come. It will strike on your aluminum workpiece. After few months, you will get you will observe that small craters will form on this surface, or material removal will happen on that surface. Okay, so this is called, or this is named as abrasive water jet machine. Okay, understood? Understood? Say yes or no so that I can proceed.
Yes, sir.
Okay, same. Whatever the destructive phenomena is there, the destructive phenomena, just a researcher or the people, they have converted for the, or that destructive phenomena is used for the constructive purposes only. Okay, and they have given the name as water jet machining and abrasive water jet machining. Okay, now come to the third process. Okay, now in the third process, if you see here in the third diagram, if you see here, you can make use of again that destructive phenomena for the some constructive purposes. Okay, again you can use destructive phenomena for the constructive purposes. People have taken the inspiration from such phenomena, and which the people have taken the inspiration from this destructive phenomena. Okay, and they saw what are they saw in daily life, what are the destructive phenomena they have used, and they have developed the process, another process. It is called abrasive jet machining. Abrasive jet machining. Okay, now abrasive jet machining is what? Now instead of that water, I am passing the air. I am passing the air through the, I can say pipe, or I can say this nozzle. Okay, I am passing air through the this nozzle, and before striking that air on the stone, I am mixing the abrasive particle. Okay, नोझल बसून ज्या टायमाला एअर बाहेर पडणार त्याच्या आधी एअर मध्ये मी अब्रेसिव्ह पार्टिकल मिक्स करतोय. ओके, अँड देन this abrasive jet is going to strike on the stone, or I can say the workpiece. Same again, due to the kinetic energy of that abrasive jet, the erosion will start at the surface of stone, and small craters will start to form. Okay, small craters will form on this surface. Okay. Now here I have taken the stone because that is a brittle, or I can say hard material. Okay. Now if you use the water and if you try to cut the stone, then that is very difficult. But if you use the abrasive jet, that means the air plus abrasive, then it is very easy to cut or to machine the stone by this method. So this destructive phenomena used and you converted for the constructive purposes, and this process is named as abrasive jet machining. Okay, abrasive jet machining. Okay, you can take aluminum instead of stone, and you can pass the air plus abrasive. You can strike that jet on that aluminum. You will get the scatters here also. Okay, no problem. Okay, so from this you can from this three diagram 1, 2, 3, you will realize that how the researcher of the people use such kind of destructive phenomena, and how they have utilized this destructive phenomena for evolving or for developing the advanced machining processes, or for developing non-conventional machining processes. Okay, again they have put this phenomena in very delicate and sophisticated way. Okay, that is the advanced machining processes. Okay, in detail this how that in detail again working principle, setup, and what are the components or the elements of this all machining or machines, I can say machines. That part we are going to cover in the chapter number 2. This is just a overview. Okay, from this I think from this three diagram and whatever I explained just now, from that 100% you got the idea about these three processes. Okay, have you got the idea about the mechanical energy based processes? AJM, WJM, AWJM. Say yes or no.
Yes, sir.
Yes, sir.
समृद्धी, नानासाहेब.
Yes, sir.
Okay, Athar, Jaydev. Have you got this concept? I will say concept behind this water jet machining, abrasive jet machining, abrasive water jet machining. Very simple concept. Okay. We have taken the example also. What are the events which we are seeing in our daily life? Okay. So these are three processes. Okay. Will you please draw these three diagrams within 2 minutes? Because in our subject only diagrams are there, and without diagram there is no weightage for your writing. Okay, if there is a question for 5 marks, and if you draw the diagram, you will get 2 marks, and for explanation 3 marks. But if you write only explanation, you will get only 2 marks. Okay, otherwise no one will give more than 1 mark, because from diagram you will be able to describe, or you will be able to explain the concept. Again, okay, before drawing this diagram, I will here tell, or I will give the instruction. Now, what are this diagram I have used in this my presentation? It is belongs to the advanced machining process by VK Jain book. Okay, for each and every diagram I am going to give the reference, because in each and every book, or I can say that if you take an example of VK Jain book, or ZBSA book, or another Hassan Ilofi, okay, you will get the different diagrams, but the whatever the concept or fundamental is there behind the every process, it is same. मी आता इथं कसं नळ आणि पाण्याचं एक्झाम्पल घेतलं, दे विल गिव्ह द अनदर एक्झाम्पल, बट there will be the water, and there will be the work, and there will the kinetic energy, and there will the that scatter formation. Okay, that concept is not going to change. Okay, but for the simplification of the our concept, you can create your own diagram also, no problem. Okay, but concept should not be changed. This diagram I used from the VK book. Okay, so you should know. Okay, can you draw this diagram within 2 minutes? I think a diagram is clearly visible to you all. Okay, please draw this. I will give 2 minutes only. And please write down that velocity of average water jet as high as 900 meter per second. Here at bottom I have used I have written that statement. How does it work? That means these 3 processes. For the water jet machining, kinetic energy of water used. For AWGM, kinetic energy of water and abrasive particle used. Okay, and for AJM, kinetic energy of abrasive particles used. Okay, now in AJM, that air will act as just a carrier gas. Air will be act as carrier gas for the abrasive particles. Okay, you will come to know that during our next lecture, because in next lecture I will start the AJM. Don't worry. Okay, shall we proceed for further?
Yes, sir.
Okay. Now we'll go for the another one, advanced machining processes, which is belongs to the mechanical energy based processes, that is ultrasonic machining. Okay, ultrasonic machining. Okay, this is again this ultrasonic machining, it is also belongs to the mechanical energy based processes. Now how that belongs to mechanical, that concept I will explain here, don't worry. Okay, now in this ultrasonic machining, here you have the tool, you can see here this sky blue, or you can say navy blue color. This is a tool, okay, which is vibrating at ultrasonic frequency. This tool is going to vibrate in longitudinal direction at ultrasonic frequency. That means near or I can say more than 20,000 hertz. Okay, means 20,000 times per second. It is vibrating with a certain amplitude of the vibration. Frequency term is different, amplitude is different, but we require both terms for this. Okay, this tool is going to vibrate near about or more than 20,000 hertz. Okay, and with a certain amplitude of vibration. And here, if you see here, there is a slurry. Now we are going to supply the slurry. Slurry means what? Here we are going to take liquid carrier plus abrasive particles. Abrasive particles I am going to mix with the liquid, and that abrasive slurry I am going to use in between workpiece and the tool. Now here I want to highlight the one point. In conventional machining, we are using physical tool. Okay, and that physical tool is in contact, physically in contact with your workpiece, physical contact. But here we are using tool. Okay, because this I'm saying this tool, and I'm using this tool, but I'm going to, or I'm keeping some interrelated gap, or I can say gap between this tool and your workpiece. And in between this gap, I'm going to take, or I'm going to flow the flow of abrasive slurry. Okay. Now this slurry consists of the liquid. Liquid means what? You can say water plus abrasive particles, no problem. And when this tool hurts or I can say this tool, when this tool is going to hit the this particular abrasive particles, then it comes and strike with the workpiece. Okay, due to the vibration of your tool. Okay, with more than 20,000 hertz vibration. Okay, that frequency, this abrasive particle also going to vibrate. Correct. Okay. Now, then due to the vibration, again this abrasive slurry particles is going to strike with the workpiece. Say here ceramic is the workpiece material. Okay, and so due to that 20,000 hertz frequency, or I can say 20,000 times, okay, abrasive particles are going to hit this workpiece, ceramic workpiece. Okay. Okay. Now this so thousand particles example ceramic it strikes ceramic or a workpiece material, and they will start or they will remove work material in the form of very fine crater. Okay, very fine crater. That means small particles will start to remove from this ceramic work material. Due to what? Due to the impact of, or due to this hitting of abrasive particle. Now that hitting will happen due to the vibration of this tool. Okay, vibration of this tool. Okay, tool. Okay, and craters will, that's very small crater or fine craters will form on this surface, and material removal will happen. Okay, now you know that why I have taken the ceramic workpiece, because here I want to tell you that here you can take hard material, you can machine that hard material using this ultrasonic machining. Okay, now when you want to, now take an example. Now you want to cut the workpiece surface, or that you want to give a half circle shape or curvature shape on this ceramic. That time you have to continuously vibrate your tool, and due to that vibration, abrasive particles are going to hit that surface, and you will get the whatever the desired surface. Okay. Now, how you will get that curvature part? For that purpose, here is one small requirement is there. What are the desired shape you want on your workpiece? That same shape you have to give to your, or very close shape you have to give to your tool also. Okay, you have to give the same shape or close shape on your tool. Okay, whatever you want on your workpiece. वर surface वर जो shape तुम्हाला पाहिजे, it may be half circle, it may be drilling, okay, or it may be the rectangular hole also. The same, or I can say close to that, you have to give the same shape on your tool also. Okay, to get the desired shape on the workpiece. Okay, so this is used, or now this ultrasonic machining is used for the machining of brittle and fragile materials. Okay, which we will discuss during the chapter number 2 also. Okay, here I have explained just the basic concept behind this ultrasonic machining. Okay, have you got the concept? Say yes or no. इथं काय केलंय मी, एक टूल घेतलंय
येस सर.
आणि त्या टूलला मी काय करतोय, व्हायब्रेशन देतोय. आता व्हायब्रेशन कसं द्यायचं, तर ते काय डीसी पल्स वगैरे आपण वापरणार आहे, ते डिफरंट वापरून आपण बघणार आहे, नो प्रॉब्लेम. काय करतो, त्या टूलला मी कंटिन्युअसली, दॅट मीन्स मोर दॅन 20,000 हर्ट्स फ्रिक्वेन्सी ना, अगेन विथ द सम सर्टन अँप्लिट्यूड मी काय करतो, व्हायब्रेट करतोय. आणि मी काय करतोय, तुमचा वर्कपीस आणि टूल मध्ये थोडा गॅप ठेवतोय. किती गॅप ठेवायचा की इन डिटेल आपण बघणार आहे. ओके, आणि तो गॅप कंटिन्युअसली तेवढा मेंटेन करायचा. म्हणजे वर सरफेस जसा जसा फिनिश होत जाईल तसं तुमचं टूल खाली येणार. ओके, किंवा फॉर एक्झाम्पल 10 mm जर तुम्ही गॅप ठेवत असेल तर ती कंटिन्युअस तेवढा मेंटेन करा. त्यासाठी तुम्हाला वरती सेन्सर वगैरे लागणार आहे, टूल होल्डर वगैरे, ते पार्ट आपण बघणार आहे. ओके, आणि ड्यू टू दॅट व्हायब्रेशन इट विल पास टू द युअर slurry, abrasive slurry. म्हणून मी abrasive slurry मी इथं पास करतोय. ओके, abrasive slurry means what? It is just a mixture of water and abrasive. Now again question arises, abrasive तुम्ही काय काय घेऊ शकता. तर इथं आपल्याकडे डिफरंट abrasive आहेत, त्यांचं ती कुठल्या abrasive कधी वापरायचं हे इन डिटेल आपण त्या टायमाला बघणार आहे. डोंट वरी. ओके, आणि कुठली प्रोसेस हे कुठल्या मटेरियल साठी सुटेबल आहे हे तो आपण बघणार आहे. डोंट वरी. ओके, हिअर आय हॅव जस्ट गिव्हन एक्सप्लेनेशन अबाउट द बेसिक कन्सेप्ट. ओके, and I think you got this concept. Okay, shall we move? Otherwise here I will give the one example. तुम्हाला सॅन्ड ब्लास्टिंग तर माहित असते किंवा शॉर्ट ब्लास्टिंग वगैरे, ते काय करते तो, ते आपलं एक स्मॉल हे असतं बॉल, ते कंटिन्युअसली तुमच्या कास्टिंगचं जे आहे प्रोडक्ट म्हणजे जस्ट फाउंडरमध्ये बाहेर त्याच्यावरती काय करतात, कंटिन्यू पास करतात. का तर त्याच्यावरती त्यांना ते बिनकामाची जे आहेत काय म्हणतो पार्टिकल्स ते बाहेर काढायचे. सेम कन्सेप्ट. ओके, आता इथं फक्त आपण काय ते कंटिन्यूस ट्राय करत नाही. ओके, फक्त आपण काय तर व्हायब्रेशन मुळे ते काय होणार, ॲब्रेसिव्ह स्लरी किंवा ॲब्रेसिव्ह पार्टिकल व्हायब्रेट होणार आहे. आणि त्या व्हायब्रेशन मुळे हिटिंग होणार आहे. कोणावरचं हिटिंग HIT. ओके, त्या वर्क सरफेसला हिट होणार आहे. ओके, and due to that scatters will form, or I can say material removal will happen. Okay, now we'll go for the next one. Take 1 minute to draw this diagram. Take 1 minute. And during this particular processes, I'm going to show after my explanation during that time. I'm going to show the practical examples. Okay, also about this actual process through YouTube video also. Don't worry, or animation video. Now let us move for the next one. Now there is another process called electric discharge machining. Now this electric discharge machining belongs to the electrical energy based processes. Now let us see. First I will explain you how it is evolved. So we'll go for history or background about this process. Now there were two brothers. The name, their name was Lazarenko brothers. Okay, Lazarenko brothers. Okay, in the old USSR. Okay, that is the name of the country. And one day they found that male and female parts of their switches. Okay, you can see here male and female part of the switches. Then they were having the dark metals and dark spot were there. Okay, you can see here also dark or worn out marks are there. Okay, on this male and female part of the electrical switches. Now they have observed that some metals has been removed from the male as well as the female parts. Okay, male as well as from female parts. They have observed that some materials has been removed, and then that both brother, that means Lazarenko brother, started thinking that how to make use of this destructive phenomena of the sparking for some constructive phenomena. Now already we all know that about that due to the sparking, material removal or burning of material will happen from the wire surface, or I can say the switches also. Okay, so due to that, dark marks or worn out marks will be there. Okay, so this destructive phenomenon of the sparking they have used for the constructive purposes, and then they kept trying for years together. Okay, same destructive phenomenon. From that they have started thinking, and they have started different experiments. Okay, for years and years, and then they have developed many machines, but none of them worked properly. Okay, so using this phenomena they have developed different machines, many machines, but none of that machines worked properly. Okay, then finally after long time they were able to develop a machine which is named as electrospark machining. Okay, firstly for many experiments they got machine, but that are not working properly. But after a long time they have developed, or they were able to develop a machine which is working properly, and they have given the name as electrospark machining, and nowadays or today it is known as electric discharge machining. Okay, what was the concept? There were two components of electric switches, male and female, and there were a spark happened in between that, and due to that sparking, metal removal happened from both the surfaces, and this phenomenon they have used for developing the machine, and they have developed the machine, that is EDM. Okay, now after development they have patented it. Okay, they have patented it, and the working principle of this machine is very simple. Okay, suppose Now you can see here in this diagram. Suppose you have a tool, okay? Over here you have a tool, okay? This is a tool, and you have the workpiece. This is a workpiece. In between this tool and the workpiece, you can flow what is known as dielectric fluid. You can flow the dielectric fluid. Okay, now that dielectric fluid means you can use as a water or the kerosene. Between this tool and the workpiece, you have to maintain gap, and in between that gap, you have to flow the dielectric fluid. And that dielectric fluid means what? Kerosene, or it may be the water. Okay. Now, after that, what you have to do? You have to connect this tool and workpiece to your DC power supply or pulsed power supply. Okay. So you can give this negative terminal of cathode, you can say, to the you can mention this tool as a cathode and this workpiece as a anode. Okay. Positive point, the positive terminal it is connected to the workpiece. Negative terminal it is connected to the tool. Okay. And when you start the passing current, okay, when you start the switch, you can see, okay, or you can on the switch, then potential gradient between these two electrodes. Now I am saying the electrode. Negative electrode means what? Tool. Okay, and positive electrode means the workpiece. So here potential gradient in between these two electrodes will be developed, and that potential difference in between these two electrodes will be the more than the breakdown voltage of the dielectric fluid. Okay, more than the breakdown voltage of the dielectric fluid. Then plasma columns is going to form. Plasma column is going to form between these two, and sparking will take place. Okay, whatever the potential gradient is there in between this tool and workpiece, that is more than the breakdown voltage of the dielectric. Then due to that, plasma column is going to form between these two, and sparking takes place. And because of that sparking, the material is going to remove from the tool as well as this workpiece. Material is going to remove from this tool and the workpiece. And finally, you get the shape of the cavity on the tool workpiece, which is very, very close to the your shape of the tool. Okay, but mind it here, material is being removed from the tool as well as the workpiece. Okay, here material is going to remove from the your tool as well as the workpiece, but whatever the quantity of material is going to remove from the tool, it is very less as compared to your workpiece. Okay. Okay, got it? This is called the electric discharge machine. What you have to do? You have to take a two electric conductive materials. Why I am saying electric conductive material? Because you have to pass the current, or you have to create or you have to maintain the potential difference. Okay, for that purpose, here the basic requirement of this electric discharge machine is that both your tool as well as workpiece material should be electrical conductive material. Okay, and you have to connect your tool to the negative terminal. That means your tool will act as cathode and workpiece will connect to your positive terminal. Okay, pulsed DC power supply. Okay, and you have to maintain the small gap, and that small gap is called inter-electrode gap, IEG, inter-electrode gap. And in between this inter-electrode gap, you have to pass the dielectric fluid, and that dielectric fluid will complete your circuit. Okay, and here your potential gradient will be more than the breakdown voltage of your dielectric fluid, and due to that spark will happen, and due to that sparking, material removal will happen from this workpiece as well as the tool, but that quantity is very small. Okay, so this is called the electric discharge machine. Got it? Understood or not? Here I mentioned, I have discussed the basic concept. Okay, again, working principle in detail. Also the what are the different components of this setup or machine. That part we are going to cover in the chapter number 3. Okay, we have the separate chapter for this electric discharge machine. Yeah? That is third chapter. Now, have you understood the basic concept behind this EDM process? I'm saying in short, EDM, electric discharge machine. Understood? Say yes or no, some students.
Yes, sir. Yes, sir. Yes, sir.
Okay. In simple language, I'm explaining you all. Girl students, from girl students, say yes or no. Girl students, say yes or no. Joshi. Joshi, Deshpande. Then who's this there?
Yes.
Okay. Will you draw this diagram, all of you? हा, कुणाला काय शंका असेल ते विचारावे बा, काय प्रॉब्लेम. हा, आता इथं आता मला एक सांगायचे, जो इंटरनेटवर गॅप आहे तो किती मेंटेन करायचा. ओके, कंटिन्युअसली. हा, ते आपण इन डिटेल बघणार आहे. अगेन डायरेक्टली फ्लूइड कुठलं वापरायचं, का वापरायचं, त्याच्या प्रॉपर्टी काय असणार आहे त्या. ओके, आणि ज्या टायमाला तुमचं वर्क मटेरियल कुठलं असणार त्या टायमाला डायरेक्टली फ्लूइड कसं वापरायचं, सॉरी कोणतं असायला पाहिजे, डायरेक्टली फ्लूइड कसं पास करायचं. सो फॉर दॅट अगेन वी हॅव द डायरेक्टली methods. Okay, in detail we are going to see in the chapter number 3. Don't worry. Okay, then how we are going to maintain that gap. Okay, tool material कुठलं पाहिजे. Okay, in detail again we are going to see in chapter number 3. Don't worry. Please draw this diagram within 1 minute. Please note down, for this electric discharge machining, both your tool and work material should be electrically conductive material. Here non-conductive material, machining of non-conductive material is not possible using electric conductive material. Electric discharge machining. In previous lecture, during my previous lecture, already I have mentioned that none of this all advanced machining process is suitable for all the conditions. Okay, for each and every machining have their own characteristics. Okay, so after studying one by one every process, you will get which process is going to suitable for which material. Okay, you will come to know. Okay, shall we move forward further?
Yes, sir.
Okay. Now we'll start the part number 2. Okay, of this our overview of non-conventional machining processes. Okay. Now this is another interesting thing. Okay, that is a laser beam machining. Okay. Again, for this laser beam machining, I will take the example, or I can say the interesting thing which children in their child age, or rather I will say all of us in our childhood age, we have performed this experiment. Okay, or now what we were doing. Now this concept we were looking as a magic. Okay, during our childhood. Okay, so what we will doing? We were taking a lens, correct? Lens. So in this figure I will show you this is a lens. Then we are trying to concentrate the sun rays through this lens, and we are trying to strike this sun rays or concentrate the sun rays on this piece of paper. And after some time, what you will observe? Burning will happen, and then that experiment we were enjoying as a magic. Okay, that burning of the piece of paper using lens, and by concentrating the sun rays through that lens on the piece of workpiece, after some time that piece of paper is going to burning, and that we were saying as magic. Okay, but that is not a magic. That is a one of destructive phenomena. Okay. Okay. Now similar kind of concept, researcher or I can say people has been utilized for the constructive purposes. If you see here, okay, if you see here in this second diagram, okay, in case of I will take a direction name, that is in case of laser beam machining. Okay, you are doing, or sorry, you are concentrating the laser light. Now instead of the sun rays, we have to take the laser light or laser beam. Okay, here through this laser gun you can take the laser beam, and then through this lens, okay, having very small, okay, that portion, through that you can pass the laser beam on the workpiece. Okay, same concept. Now where you are going to pass this laser beam? Where you want to remove the material, on that surface only you have to pass the laser beam. Okay. Now through this laser beam, when passing through the lens on this particular portion of the workpiece, after that, due to the intensity or high heat intensity of this laser beam, okay, or laser light, high heat intensity of laser light, the melting, or I can say melting and vaporization will start, and due to that melting and vaporization, material removal will happen from this workpiece. Okay, what you use or what you have done for this process? You have taken laser beam, and that laser beam you have passed through the lens or on the small portion of the workpiece where that workpiece to be machined. On that workpiece you have concentrated that laser beam. Okay, and due to the high heat intensity of the laser light, melting and vaporization is happened, and work material removal happen on this work surface. Okay, this is called the laser beam machining. Okay, now heating will happen because of high temperature of your laser beam. Okay, so now the temperature and other thing we are going to see in the chapter number 5th. Okay, sorry, in chapter number correct, 5th. Okay, so through this machining also, through this process, you will get the desired shape and size. Okay, you can pass this laser beam or you can use this laser beam machining for the materials which is difficult to machine material and having the high thermal conductivity. These two properties or two words is important. Difficult to machine material. Okay, for that purpose you can use this laser beam machining, and material having the high thermal reflectivity. Okay, That means you can use for the aluminum, then copper. Okay, but here using this laser machining, you will get the very low machining efficiency. Okay, very low machining efficiency, because continuously you have to concentrate your laser light or laser beam through the lens on that your workpiece. Okay, where you want desired shape. Okay, so here very low machining efficiency you will get. Okay, okay, that machining efficiency may be 1% or more than less also. Okay, so this machining process is not suitable for every example, but for the high thermal conductivity as well as for difficult to machine material, again for high reflectivity material, you can use this laser beam machining. Understood? Say yes or no. Okay.
Yes, sir.
For every process, I am giving an example of our day-to-day life event or incident, or the whatever our magic things. Okay, which we were doing at our childhood age. Okay. Now let us move for the next one. There is plasma arc machining. Okay, this is another process called as plasma arc machining. Now that laser beam machining and the plasma arc machining, electron beam machining and ion beam machining, these are belongs to the thermoelectric or thermal energy based processes. Okay, now I will give explanation about the plasma arc machining. Now in this particular, as you can see here in this figure, we have the gas. Okay, you have the gas which is coming in. Okay, which is coming in, and it is connected to the electrode. Okay, now here you can see here this is the electrode, and from this you are passing or we are passing the gas. Now this electrode is connected to the negative terminal. Okay, to the negative terminal of your DC supply, and here is the workpiece. Okay, you can see here workpiece is there, and that workpiece is connected to the positive terminal of your DC supply, positive terminal. Okay, and then we are going to apply very high potential in between this positive and negative, or I can say in between this electrode and the workpiece material. And when this gas comes, then arc is formed, and then gas gets the ionized and plasma is going to form, and then this plasma has a very high heat intensity, and you can cut the any material due to that very high intensity plasma. You can cut any material, okay, that you want to cut. Okay, and when we want to cut very thin materials where electrical arc does not work, that time or at that place, we can use this plasma arc cutting for the cutting of those thick materials into the pieces. Okay, what is the basic principle? Once again I will repeat. We have to take the gas, we have to send gas into here. Okay, so here electrode also is there, and that electrode you have to connect with the negative terminal of DC supply. Then your workpiece is going to connect to the your positive terminal. Then when you pass the gas, then arc will form, and due to that arc, gas is get started ionized, and plasma is going to form, and due to that plasma having the high intensity, you can cut any material. Okay, so wherever it is not possible to cut the thick material using the electric arc, you can use this plasma arc cutting machine. Okay, in syllabus the name is given plasma arc machining, but in practically plasma arc cutting is the famous word. Okay, so this is a very interesting, very useful process, but this process is used for rough machining only, not finishing machining. Okay, this is used for the rough machining or for rough cutting. Okay, not for finishing machining or finishing cutting. Okay, so you can use for softening of workpiece by heating using a plasma arc. Okay, or can say plasma arc cutting also. Okay, got it? Now this part we are going to cover in detail about this plasma arc machine. We are going to see in the okay. Got it? Understood or not? So that I can go for next one.
Yes,
Say
sir.
yes or no.
Yes.
Yes, sir.
Okay,
Yes.
sure. Next one. Now another one which is belongs to the again thermoelectric or electric energy based non-conventional machining process. Okay, there is a electron beam machining. This is again very interesting process, electron beam. Okay, now you can see here I have shown already in some example during the what do we need. Okay, okay, for the machining of the small micro holes. Okay, here you can see here we have the electron magnetic lens. Okay, so you can see here electron magnetic lens are there. Then we have the beam control coil also there. Okay, beam control coil also is there. Okay, here electron magnetic lens, then electron control coils are there. Okay, beam control coils is there. Then you can see here this is the electron beam, which is electron in this particular beam. You are okay, electron beam. Okay, so this is the electron beam, and this electron beam are moving at a velocity which is close to the light. Okay, this electron beam is going to move with a high velocity which is close to the our velocity of light. And when such a high velocity electron, although they have got a negligible mass, okay, but with such a high velocity, I can say half of the mv square, okay, a velocity of light, then kinetic energy becomes so larger of this electron beam, and they create a very high temperature. And at the point where they hit this electron beam on this workpiece, their temperature goes very high. Okay, and due to that temperature, machining or material removal happen. Now the question arises, how we will get electron beam? For that purpose, electron gun is used. Okay, having the electron emitting hot tungsten filaments. Okay, the in detail we are going to see in chapter number 6. Don't worry. Okay. Now, whatever this process we have to do vacuum. Okay. So the condition in this machining is that whatever we have to this chamber, no, that chamber should be the high vacuum chamber. Okay, you should have, because here is the electron, this molecules of the okay, and to not get cut on your workpiece material or workpiece component. So mostly the vacuum is created in this chamber. Okay, in our non-conventional machining processes, this is the only one process where we want vacuum for the machining. Okay, so vacuum chamber is used, okay, to avoid the sucking of air onto this electron beam. Okay. Okay, so this is about the electron beam machining. So using this vacuum, we will get the as we're using here. Okay, so that vacuum can be that what I so vacuum maybe the 10 to minus 1 mm of GHG. Okay, how vacuum is there. Okay, got it. Again, to get that electron beam, we require the electron gun. Don't forget that point. An electron gun, which will have the electron emitting hot tungsten filament, and that we have to connect with the our power supply. So you can see here. Understood?
Yes, sir.
Now we'll go for the another one. The third take the example machine. This I project will we're going to see in chapter number 5. Don't worry. So I will explain about this. Now this focal ion beam here splintering off the knocking out of atoms from the workpiece surface will happen. Splattering off, or I can say the knocking out of atoms from the workpiece surface will happen by the kinetic momentum transfer from the incident ion to the large target ion. So you can see here. Here, splattering of atoms will happen, okay, from that workpiece surface. Now this splattering, or I can say the knocking out of the atoms from the workpiece surface by the kinetic momentum transfer from the incident ion to the target atoms takes place, and I will explain it here that with the help of this figure also. You can see here, you can see this ion of some gas, okay, ions of the some gas is coming and hitting the top surface of the your workpiece, okay, hitting the top surface of workpiece, and you can see here it has the displacement, okay, after hitting it this ions is going to displace from that particular point, and you can see here that atom, okay, here the atoms are which are the displaced. So the energy with which ion is hitting the workpiece surface on the top surface of workpiece is just sufficient to dissociate one atom from the top surface of the workpiece. Okay, one that whatever the energy is there, okay, in the ions, okay, which are going to hit the top surface of the workpiece, that ion sufficient one atom from the top surface of the workpiece, and you can see here one ion has a dissociated also. Okay, accepted I can say. The energy of is you need to and you this one ion you can use you can okay workpiece, and from that hitting there is which is available in that ion. So due to that hitting, this dissociation, or I can say separation of work material ions, work material particles will happen. That is called the ion implementation. Okay. So this is just a step behind our ion beam machining. So at sufficiently high energy, the bombarding will happen, or I can say several atoms or molecules will be ejected out, and the bombarding iron will become implemented. That that material removal will happen. Okay. So we'll see in detail also in that particular iron beam machining lecture. Okay. Now we'll start the last part of this overview. That is we'll cover the electrochemical machining and chemical machining. Okay. Now you can see here. Now there are you be knowing about the plating. Okay, electroplating concept in our chemistry or during the class or this electroplating. It is just reverse of electro. Okay, for you have the tool. You can take the example. You have the tool. Actually, this tool and workpiece both are electrical. To use here so which we will discuss later on, and when this electrolyte is flowing in between, in this gap, or I can say in between this tool and workpiece gap, then after flowing that electrolyte, you can connect this tool to your negative terminal of DC supply, and you can connect workpiece to the positive terminal of your DC supply. Then current will start flowing in between this gap. Okay, in between this gap, current will start. This gap is known as inter-electrode gap. Already I have told, inter-electrode gap. And when this current is starting flowing, then electrochemical reaction will start or will take place, and as a result of that, material is removed from the workpiece, and you will get the cavity from, or rather I will say, material removal will happen, and you will get the cavity on that or in that workpiece, okay, which is closer to the your shape of the tool. Okay, whatever shape, that shape on your work, firstly you have to give also the tool. So in shape machining. Okay, now the basic principle behind this is electroplating, and with that electroplating comes from the Faraday's law of electrolysis. Okay, that law I am going to explain during electrochemical machining particular lecture. Okay, so here limitations or two important things are that our tool should be electrical. Then whatever you want shape or close to that shape, a tool. So the replica of your workpiece. Okay, so this is a electrochemical machining. Understood? Okay, understood. Now here again important thing that here chemical properties or metallic properties of the workpiece. Okay, which affect the performance of process rather than mechanical properties of the workpiece, that is hardness. So that chemical properties of the metallic properties are no barrier in this kind of process. Okay, as there are during the conventional machining, that chemical properties or the mechanical or metallic properties, these are the barriers in case of our conventional machining. So here is no barrier about the properties. Okay, understood this electrochemical machining? Say yes or no, someone, somebody.
Yes, sir.
Okay, now we'll go for the next one. Again, very interesting. There is another one process called as chemical machining or chemical milling also sometimes we are calling. So in this process, we are using the etchant. Okay, we are using the etchant. Okay, which reacts chemically with your workpiece surface. Okay, here etchant we are going to use, which is a etchant means what? Your one chemical acid. Okay, okay, which is used for removing of the material from your work surface. So how that workpiece is going to remove? Due to the chemical reaction. Okay, to do that chemical reaction, we require the etchant. Okay, which reacts the chemically with your workpiece surface, and also you are going to use, or we are going to use a maskant. For what purpose? To hide the surface from where we do not want to remove the material. Maskant is used to hide the surface from to hide the surface from where we do not want to remove the material, and you can immerse the workpiece, or you can dip the, or you can submerge that workpiece in the etchant which already has the maskant. Firstly, you have to apply the maskant on the surface where you do not want to remove the material. Then your workpiece you have to dip, or you have to submerge into the etchant. Etchant means what? Chemical acid. Okay, and due to the chemical dissolution, or due to the chemical reaction with the help of etchant, etching will happen. Etching means what? Material removal will happen from the your workpiece. Okay, so material, so after definite period of time, the material start dissolving chemically. That means etching will happen, and after some period of time, you can take out your workpiece from that tank of etchant, and you will find the desired shape and the size on your workpiece component. Okay, so this is called the chemical machining. Got it? This is called chemical machining. What is the requirement of this process? The requirement is that you have to use the chemical rather chemical acid, rather than that I will say etchant. Okay, for the etching action. Etching action means what? Chemical dissolution, and you have to use the another one, maskant. Okay, to hide the surface where we do not want to remove the material, and you have to dip your workpiece into the tank of etchant, or you can spray your etchant on your surface or workpiece surface, and after some period of time you can take out your workpiece from that etchant solution, and by cleaning you will observe that you will get your finished component. Okay, with the desired shape and size on that component. Okay, understood?
Yes,
Here,
sir.
up till now we have covered all our whatever the processes we are going to cover in the next 4 chapters. Okay, so whatever part or whatever the theory, diagram, or the concept I have delivered in this lecture. So for that I have taken the reference of Advanced Machining Process book by V.K. Jain. Okay, so this is about the overview of our advanced machining processes or the non-conventional machining processes. So again, I want to highlight the instruction that already this total lecture I have covered through my YouTube lecture also, YouTube Premier lecture. So day before yesterday's lecture and yesterday's lecture. So within that 15 plus 15 minutes, I have covered this entire theory, entire lecture. Okay, if you have missed that, or if you have not understood in this my lecture, you can watch that lecture also, no problem. Same I have explained there. Okay, again within a short time. Okay, with clear voice and with highlighting also. Okay, I know more than 12 students or near about 15 students every day they are watching or they are connecting with me during my YouTube lecture also. Okay, so thanks for that also. Okay, understood. So here with we have successfully completed our chapter number 1. Okay, so if you have any suggestion or if you have any doubt, please ask me, or you can give feedback also you understood or not, so that I can proceed further. Understood?
Yes, sir.
Okay, so just I will share chat box. Okay, please. Unknown sender erosion here means not erosion, erosion, erosion. Now I will write that comment also. Erosion. Whether my voice is not clearly audible to you all. Rhythm has given the comment. Whether
Yes,
my
sir.
voice is audible?
In,
Okay.
there was some breaking. Your voice is breaking.
But now whether my voice is clear?
Yes, sir. Your voice is clear now.
Okay. Maybe due to the network issue, sometime my voice gets break. Okay, no problem. Now quickly I will go through the similarities and difference between the conventional machining and non-conventional machining. Okay, already I have covered this point in my today's YouTube lecture. So within short time we'll cover that also. Whether my slides are visible to you all?
Yes, sir.
Okay. So in my lecture, I started with about conventional machining and non-conventional machining, but this part already I have covered, so we should not invest our time on that point. So directly I will move toward the what are the various similarities between our conventional machining and non-conventional machining, because up till now we have gone for all the introduction about the conventional and non-conventional. So if you talk about the similarities between these two, the first point will come that both are the machining processes, because under the manufacturing manufacturing process we have the metal removal processes. So both are the machining processes and both are used for the conversion for the removal of the excess material. Okay, then both are the successive manufacturing processes. Okay, top down approach is used. Okay, both are the successive manufacturing processes. Then already I am discussed that these both conventional and non-conventional machining both are secondary manufacturing processes, and important that both can produce the sufficient smooth and finished surface. Okay, both can produce sufficiently smooth and finished surface with closer tolerance. Okay, although different processes have different capability. Okay, okay. Due to the limitations of conventional machining, we are moving towards the non-conventional machining. Okay, so these are the few similarities between the conventional and non-conventional. Okay, now let us move for the important point, that is the difference between the or comparison between the conventional machining and non-conventional machining. So here I have made two columns. In first column you will get the points regarding conventional. In second column you will get the points regarding non-conventional. Now first point about conventional machining is that only now all these points already I have explained during my last lecture in main characteristics. Okay, so same points are there, but here in different format I have mentioned. So in conventional machining, only chemical energy or chemical power is utilized to gradual remove the excess material from the workpiece. Only chemical energy, only mechanical energy is used. But in case of non-conventional machining, various forms of energy is used. Various forms of energy means what? Chemical energy is there, electrical energy is used, mechanical, light also, or I can say combination of two or more such forms are used or are directly utilized for the removal of the excess material. Okay. Then in conventional machining, materials are removed in the form of tiny sharper chips. Okay. But in case of non-conventional machining, so-called chip is not produced here. Material is removed in various forms such as tiny metal particles, ions, or molten or vapor. Okay. Then in case of conventional machining, shear deformation is the only phenomena that causes the removal of material. Okay. So shear deformation means what? Using your edged cutting tool, sharp edged cutting tool, using the physical contact with your tool and workpiece, you are applying the force, that is shear deformation. But in non-conventional machining process, shear deformation plays an insignificant role in material removal in most of non-conventional machining processes. So instead of that shear deformation, in case of non-conventional machining, we have erosion, chemical dissolution, then evaporation, splattering, etc. occurs. In case of conventional machining, we are using the sharp edge shaped cutting tool having specific geometry, material, and the property is required for the cutting action. But in case of non-conventional machining, so-called cutting tool does not exist here. Okay. However, in few cases, for example, electrochemical machining or electric discharge machining, tool is required. Okay, but by keeping the interlateral gap, and it's a profile of the property must match with the requirement. That is basic condition. Then conventional machining, about that, physical contact between the cutting tool and workpiece, and also the relative velocity in between them are indispensably necessary in order to remove the material. This is a condition. In case of non-conventional machining, although no physical contact occur between the cutting tool and workpiece, in few processes such as abrasive jet machining, abrasive water jet machining, or ultrasonic machining, solid abrasive glitz means what? Small particles, they will strike the workpiece surface for the erosion action or to erode the material. Now conventional machining, these processes are age old, and thus physics of these processes are well known to we all. So labor are also readily available at comparative cheaper cost. Okay, this is general point. But in case of non-conventional machining, achievable surface finish is much better than that of conventional processes. It can easily provide surface finish. So in case of non-conventional machining, most of the processes are developing. So labor cost is also high due to the less number of skilled labor available in the field. Conventional machining, it can provide a wide range of surface finish depend on process that is employed and also the process parameters. However, getting surface finish below the 10 micron is quite difficult. Conventional machining, you can use you require costly CNC machine. For conventional, non-conventional machining, using that you can achieve surface finish much better than that of conventional machining. Okay, it can easily provide surface finish in a nanometer range also. Okay, so conventional machining process are suitable for bulk removal of material. In this sense, these are fast, reliable, and economic. That means a higher removal rate will get. But non-conventional machining are suitable for highly accurate and precise requirements. For bulk removal of materials, these processes are time consuming, less reliable and uneconomic. So, in case of convection machining, there are certain shapes that cannot be produced by convection machining because as we know that there is a limitation about convection machining, that is to machine a complex shape or integrate geometry. It is difficult, but non-conventional machining processes sometimes become reliable option for the producing complex shapes, integrate size and shape. Okay. The last is the examples of the conventional machining. As we know that turning, facing, grooving, drilling, boring, ramming, shaping, planning, then milling, honing, lapping, grinding. These are the examples of the conventional. And the examples of non-traditional, non-conventional machining are abrasive jet machining, water jet machining, abrasive water jet machining, ultrasonic machining, electric discharge machining, electrochemical machining, chemical machining, plasma, arc machining, electron beam machining, laser beam machining, ion beam machining, or I can say hybridization of above all processes. Hybridization means what? Combination of these all more than two processes. That is called the hybridization. Okay, that is not part of our syllabus. Okay, so here is we have covered the comparison, or I can say difference between the conventional machining and non-conventional machining. For this, I will refer this references. Okay. Thank you. So here we have covered first chapter. In my next lecture, we'll start our chapter number 2. Okay. Have you got what I taught today?
Yes, sir.
Okay, understood. So as 30 students are there only, so I will take the attendance by taking the roll number of present student only. So 1 minute. Today is 26. Present roll number. One by one, I will ask. Otherwise, one by one, you can tell your roll number. One by one.
Sir, 10.
Division wise, A10 na?
B.
B10. Okay. Next.
B26.
B26. Next.
B22. B23.
B23. Next.
B11.
B22. B27. Next.
B11.
B11. Please, after giving your roll number, please unmute yourself. Sorry, mute yourself. After B11, B23 covered, B22 covered, B27 covered, B11 covered.
B47.
B47 covered. Next.
B17.
B17 covered. Next.
B41.
B41 covered. B41 covered. Next.
B16.
B60 something. B16.
16.
Okay. Next.
B31.
B31. Next.
B2.
B2. Okay. Next.
B37.
B37.
B20.
B20. Next.
B1.
B1. Next.
B3.
B15. Next.
B3.
1 minute. B54. B54 is there? 1 minute.
Yes,
1 minute.
sir.
Okay. Now, please, girl students only will announce their roll number. Other, please mute yourself. Girl students, tell.
B3.
B3, B6. Next.
B5.
B5. Next. Pranay.
A50.
A50. Next.
A20.
A20. Next.
B12.
B12 or A12? B11 is there.
A46.
1 minute. B11 is there.
No.
That time I written 11. B12 written, no problem. A division.
A3.
A
3.
20 complete, 3 complete. Next.
46. A46.
A46 cover. Next. A05 cover. A05 cover. Next. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Only 25 students have given attendance. Please, another 5. TB33. Next one. B13. Covered.
B55.
B50.
5.
B55. Okay.
B54.
B41 covered already. B50. 51. B40. 1 minute. 44. Which division?
B division.
B division 44. B16. Who is 16 covered? B34. I think 1 minute. B34. Who is the B34?
Sir, Madan Patil.
Okay, no problem. Next, I think one more student. B55. Covered. Next. Is anybody remain? कौन राहिले का बाबानो? Please, Abhinay, please stop recording.